for being with us today. Appreciate it.
Thank you, Gianluca, for the very nice introduction and for also the invitation to be one of the speakers. I'm sort of coming full circle as an ICME alumna. So you know, it's great to be back virtually back at Stanford after about 10 years or so. So the title of my talk today is Computational Methods in Ice Sheet Modeling for Next Generation Climate Simulations. And so I'd actually like to start with this with acknowledgements. Usually people have this at the end, but there's so many folks contributing to this that I don't have room on the title slide. So I'd like to kind of get this out of the way at the beginning. So this has been the result of a multi-lab, multi-university project that has been going on through about from about 2012. And so we've had several labs and several universities involved: Oak Ridge, Sandia, Los Alamos, Berkeley National Lab, as well as a handful of universities like University of Michigan, UT Austin, and NYU. And the folks that are listed here at the top are some of the team members on this, and the ones that are in bold are the ones who contributed to some of the content I'll be showing. So Luca Britannia, Max Carlson, Mauro Perigo, Andy Salinger, Ray Tumanaro, and Jerry Watkins from Sandia, Irina Demeshko, Matt Hoffman, Steve Price, and Tong Zhang from Los Alamos. And then also Kyle Shan, who was actually an ICME student when we worked with him. He's currently at Micron Technology. Oops. All right, so here's the outline of the talk. I'm going to start by giving a fairly lengthy background, since I think probably this application area is a little bit new for most of the audience members. So I'll give some motivation for climate and land ice modeling. I'll talk about ice sheet, Earth system models and some of our projects for ice sheet and Earth system modeling. I'll show you the equations we use to solve when we model land ice, and then I'll talk about some of the codes we've developed for solving these equations. And then the second part of the talk, so what I decided to do is to sort of step through some of the algorithms and software that we've developed as a part of this large interdisciplinary project, to give you a sense of kind of what it took to really get this this model that we developed to have the capabilities that it needs to have. And the hope here is that I'm going to cover a lot of different topics, and hopefully, regardless of what your area of expertise is, that you'll find something that you can really kind of connect with. And I'll at the end I'll show some kind of fun movies of simulations that climate scientists are doing with these models that I'll be talking about. Okay, so the first thing I wanted to get into is to motivate a little bit some of this work. So climate change has recently been declared a national security issue by President Joe Biden. If you look at the data, global mean sea level is rising at a rate of about 3.2 millimeters per year. And this rate is increasing with the latest studies suggesting a possible increase in sea level between 0.3 and 2.5 meters by 2100. And the sea level rise is largely due to the melting of the polar ice sheets. So when we're modeling the ice sheets, we're primarily talking about Greenland and Antarctica, which are the largest ice sheets on Earth, and they store most of the fresh water that's currently frozen, and the melting of those ice sheets is what would really kind of cause the most significant rise in sea level. And so in terms of how bad sea level rise can be, if you were to have a full deglaciation, so if all the ice sheets on Earth were to melt, your sea level would rise about 65 meters, which is I think quite a lot. So most of this would come from Antarctica. 58 meters would come from Antarctica, which is much bigger than Greenland, and about 7 meters would come from Greenland. And this picture here, this is a NASA image that shows you in red the parts of the US that are going to be underwater if you had just 6 meters of sea level rise. And so, it's maybe hard to see here, but we'd all be underwater, and all that, prime real estate in Palo Alto would be gone. So this is a real concern. And so, hopefully this is convincing enough to sort of convince you that modeling ice sheets is really important in terms of trying to understand sea level rise and understand the local and global effects of climate change towards hopefully preventing some of those changes, or in the very least, trying to prepare for them. So let's actually talk about what is an ice sheet model. So this cartoon here on the right, this is kind of the anatomy of a typical ice sheet model. And I think of this as having three key pieces, which are shown in these three colors, the red, green, and blue. So the green piece, this is what's called the dynamical core, the die-core, and this consists of a set of partial differential equations for the conservation of mass, momentum, and energy of the ice. And so the bulk of this talk is going to focus on what these equations are and how we actually solve these equations efficiently. The other two pieces are kind of equally important. So the red piece here, this is what we call physics. These are typically parameterizations of different physical processes that are relevant to the ice sheet. And typically these would be things that you either don't have explicit equations for, or things that if you were to write down equations for them and discretize them, it would make the model so expensive and require such high resolution that it really wouldn't be feasible to run the model at continental scales. And so examples of this would be parameterizations of iceberg calving or fracture of the ice at the terminus, basal sliding, and I'll talk a lot about basal sliding a little bit later on. And then the last piece here is climate forcing. So this is basically taking into account contributions you would have to your ice sheet from things like snowfall melt, ocean melting, freezing. And the idea here is that your ice sheet doesn't just live in a vacuum. It interacts with the other climate components, things like atmosphere, sea ice, and so on. And so typically this climate forcing data is going to come from what we call an Earth system model or ESM. So what is an ESM? ESM stands for Earth System Model. The idea here is that your typical ESM is going to have 6 modular components, and so these are shown here for a particular model called the E3SM that I'll explain shortly. So you have 5 different pieces for the different kind of climate parts here: the atmosphere, ocean, sea ice, land, and land ice. And then the 6th piece is what we call a flux coupler. And so what this does is it takes these different models that are going to be developed separately according to the relevant physics and dynamics and using the appropriate discretization methods, and kind of glued together in the context of this global model. And the flux coupler will basically pass information back and forth to do the coupling in a way that ensures stability, accuracy, consistency, and so on. And so there are several of these Earth system models worldwide. I had a few of these at the bottom. The US ones are the CSM, the Community Earth System Model, which is developed out of NCAR, National Center for Atmospheric Research in Boulder, Colorado. And then the second one here is the E3SM, which is the Energy Exascale Earth System Model, and this is the Department of Energy's Earth System Model. And the model I'll be talking about today is actually hooked up to both of these, but we're primarily focusing on the E3SM since we're funded by the Department of Energy. So that's kind of a natural place for us to plug in. The goal of these models is ultimately to provide actionable scientific predictions of 21st century sea level change, including uncertainty bounds. And just to sort of motivate a little bit this project and this work that I'm talking about, just to put it into perspective, about a decade ago when I first started working on this, there was a real problem, namely there wasn't a robust enough land ice model out there that was appropriate for integration into one of these ESMs. So just to expand on this a little bit, in 2007, the IPCC, the Intergovernmental Panel on Climate Change, this is a group of scientists that meets every few years to make recommendations about kind of the status of climate change research and climate change. They issued their 4th assessment report, and they actually declined in this report to include estimates of future sea level rise from ice sheet dynamics because the models at the time weren't able to mimic or explain some of the dynamical behaviors that were happening at the time. And there's a quote here that a lot of work was needed to make these models really have the capabilities and the robustness that they needed to have. And so essentially what happened as a result of this is there was really a flurry of activity to try to bring the land ice models kind of up to the standard that they needed to be at. And so we were fortunate enough to have two back-to-back DOE-funded projects called Pisces and Prospect, starting in 2012. Pisces stands for Predicting Ice Sheet and Climate and Evolution at Extreme Scales, and Prospect is probabilistic sea level projections from ice sheet models and Earth system models. And so the work I'm presenting today is done as a part of these projects. The aim of these projects has been to develop and apply robust, accurate, and scalable dynamical cores for ice sheet models on unstructured meshes to enable uncertainty quantification and to integrate these models and tools into the DOE E3SM. And so I already mentioned the DOE E3SM, but this is basically the Department of Energy's Earth system model. They put it in place around 2013. And the aim is to again have this sort of next generation model that's going to focus on decadal to century timescale projections, high spatial resolution meshes solved on next generation HPC platforms, and looking at studying the impacts to US infrastructure. Now, how do I make this top part go away? Let's see. Oh, shoot. Okay, that's not how you do it. Well, maybe it will go away. Okay, so under these projects, we have had two dynamical cores developed. And so the one I'm talking about today, just so you kind of are familiar with the acronyms, is called MALI, which stands for MPAS Albany Land Ice. And I'll talk a lot more about this in the coming slides. Just so you're aware, there is a second dynamical core out of Berkeley National Lab called Bicycles. And so this is actually a pretty cool model as well, with its own kind of capabilities that are worth spending an hour or more on. So I won't cover this, but this is something else that we've been developing as a part of this project. Okay, so that's kind of the motivation and a little bit of the kind of programmatic background. So let me now get into some of the actual kind of technical stuff, starting with the actual equations that we use to model land ice. So it's fairly well accepted that ice behaves like a very viscous, non-Newtonian shear thinning fluid. And so this may be a little bit surprising to some of the students. You know, when I first heard about land ice modeling work, I was imagining, you know, you'd be studying, you know, fracture, things like this. We actually don't model the ice and the fracture of the ice, since it's not considered to be kind of important to the large scale motion of the ice. Instead, we model ice using these equations that are called the Stokes equations, Stokes flow equations. The way to think of this as a very viscous fluid that just essentially sits there and very slowly spreads under its own weight. So something analogous might be something like lava, or if you can imagine honey, just kind of sitting there and slowly spreading under its own weight. Typically, we model the land ice quasi-statically, and so what this means is we have a steady set of equations for the momentum balance, which is what's shown here, and these are coupled to dynamic equations for the conservation of mass and energy balance. And so I'll start with these momentum balance equations. The kind of the highest fidelity model out there, the gold standard model, if you will, is this nonlinear Stokes flow model. And so in terms of the different terms here, we have 4 unknowns per grid cell, the velocity components and the pressure. And then tau here is the deviatoric stress tensor, which is 2 mu epsilon, where epsilon is the strain rate tensor, and then mu is the viscosity. And so if you've taken a basic fluids course, this may look very familiar, and you might say, oh, well, this is just just simple fluids, simple Stokes flow. This is something we've studied many times. Well, the answer to that is not quite. And so what makes this different, what makes this actually very challenging, is the fact that this viscosity mu that's embedded in this tau term, this is highly nonlinear. Okay, so this is given by an expression that we call Glenn's law or Glenn's flow law. And so it's this very complex nonlinear expression where you have a nonlinear dependency on the temperature, which comes from another equation that I'll show a little bit later on. And then you also have this nonlinearity in the strains. And so this makes this very challenging to solve. Now I mentioned that this is the gold standard model, so that's great. Unfortunately, this model ends up being pretty expensive to solve at the continental scale. So you have 4 unknowns per grid cell. This would translate to a saddle point problem. You're going to need mixed finite elements if you're doing this, discretizing this using finite elements, or you're going to need stabilization to deal with the in-soup condition. There are other challenges, but I think I'll kind of stop there. This situation has really motivated people to look at some alternate models that are cheaper to solve than this full Stokes model, that are derived from the full Stokes equations. And so the model that we use is one such model. this model is called the first order Stokes or the Blatter-Patton model. And so the way that we obtain this is we derive this from the full Stokes equations by essentially making a hydrostatic approximation and applying a scaling argument based on the ice sheets being very thin. And when you make this argument, you get the system shown here, which we call the first order Stokes or the FO Stokes equations. And basically, this is a nice elliptic approximation of the full Stokes equations. You still have a 3D model. It now just has two unknowns, the two velocity components. You still have this nonlinearity in the mu. And this is actually considered to be a pretty high fidelity model. It's valid for both Greenland and Antarctica and can be used in continental scale simulations. So let me, before kind of going on, I wanted to spend a little bit of time talking about boundary conditions, because the boundary conditions are, as it turns out, incredibly important. They have really very significant effects on the ice behavior. And so the cartoon here on the right, this is showing the different boundaries that we have. So we have ice atmosphere, ice ocean, and ice bedrock. And so at the ice atmosphere boundary, we have a stress-free boundary condition, homogeneous Neumann. That's pretty straightforward. At the ice bedrock boundary, we have the basal sliding boundary condition. And I wanted to talk about this one a little bit because it'll come up again. And it's very, very important. And it's one of the things that causes challenges to this formulation. So this is a Robin type of condition. And what defines this condition is beta, which is the basal sliding or basal friction coefficient. Okay. And so what beta is basically a proxy for basal friction processes happening at the bedrock. And so what causes friction at the bedrock is basically ice melting. So when the ice melts, you have lubrication at the bedrock. And so in terms of this beta, when you're very much in the interior of the ice, kind of in the middle of the, middle of Antarctica here, let's say, right? That beta is going to be very large. You're going to have a lot of friction because there's very little water there. There's very little melting. But then as you go kind of near the peripheries, you're going to start to see melt there. And so you're going to have this value decrease. And so that's the case where you have not very much friction and the ice is kind of free to move around and where a lot of interesting things can happen. And so a couple of important things about beta is, first, this is a spatially varying field. So it's not just a constant, it exists at all the grid points of the on the bedrock of the ice. And then the other important piece here is that we cannot measure beta. So we need to estimate this from data we do have, which is typically at the top surface. And one of the topics I'll cover is how we actually do that in a rigorous way. And then the last piece here is the ice ocean boundary. So this is where we have the floating ice or the open ocean boundary condition. This is setting normal strains on the ice equal to the hydrostatic pressure exerted on the ice by the surrounding ocean. And this is important because it defines what are called ice shelves. And so ice shelves are really something that you see for Antarctica, not so much Greenland. So Antarctica has a lot of these ice shelves and they're shown in these different colors. You may have heard about some of these because these make the news periodically, the Ross ice shelf, for instance, which is quite big, the biggest one actually. And so what these are extensions of the land ice that just have ocean underneath, but they're connected to the interior ice, okay? And so these are important because in general, the only way you could really have a very large amount of land ice loss and a sea level rise in a short amount of time is if you lose one of these ice shelves. And that's because these things are, quite big and they could just break off. So you could potentially lose this, huge mass. But additionally, the ice shelves have the effect of buttressing the ice in the interior of the domain. And so if you lose that buttress, you're going to see a lot of the interior ice also slide into the ocean very quickly because that buttress is gone. And I'll actually show a simulation where you can see this very well towards the end. So everything I've shown so far has been steady. We want to do dynamics. And so for that, we need to bring in our energy and mass equations. And so these are shown here. We have an advection diffusion equation for the temperature, which is the energy equation. You can also write this in terms of enthalpy. And so the temperature shows up in the viscosity here, where this flow factor is a function of the temperature. So it's actually nonlinear in the temperature. And then you can see that the velocity and the strain rate and all this also appears in this equation. So it's highly coupled to the previous equations. And then we have an advection equation for the mass. And this translates to an equation for the ice thickness. And this is where we incorporate some of the source terms for the model that I mentioned, the forcings from the climate components. B dot is surface mass balance, which is basically like accumulation minus runoff. This equation is important because this tells us our geometry that we're going to solve the problem on. So the way that this is typically done in ice sheets is typically people will kind of mesh up a block of potential ice like shown here. And then you have an initial thickness, you check in each grid cell if the given thickness is, if the initial thickness is above or below a certain minimal threshold that you specify. If it is, then that cell is considered ice covered, otherwise it's not. And so then as you go in time, this changes. And so you have basically a kind of a mask that tells you which cells are active and which are not. And so this is a way to allow you to change the mesh and the geometry without having to actually throw away your entire mesh and mesh from scratch all over again. You can think of this as a kind of a level set equation if you're familiar with that. Okay, so we have two relevant codes here that I'm going to talk about for discretizing these equations. And so this is a little bit of a kind of a picture that shows you what all the relevant codes are. It's a little bit, there's a little bit much here, but so the MALI model is comprised of two codes called MPAS and OLI. OLI stands for Albany Land Ice, and MPAS stands for Model for Prediction Across Scales. So the momentum balance equations, the first order Stokes equations for our production runs, we typically rely on the Albany Land Ice model to solve these equations. We also have some capabilities to do the temperature solve in OLI, and I'll talk a little bit about this later on. But typically for the production runs, we're relying on this MPAS code to handle the dynamic equations, the energy balance and the conservation of mass equations. And I'll talk a little bit more later on about how we do this coupling, but one reason for doing this is MPAS already had a hook into the E3SM, so this was a way for us to very easily get our model coupled to the E3SM. So I'll say a few words about each of these codes on the next couple of slides. The focus on this talk is going to be on this OLI piece and the velocity solve, and that's because this is really kind of the most expensive part. So this is the part that most of our work has gone into, and this is really the part that you need to get as scalable and as fast as possible, because it's really kind of the bottleneck of the running the coupled simulations. So just a few words on each of these codes. So Albany Land Ice is implemented within a code we have called Albany, which is an open source parallel C++ multi-physics finite element code. It's available on GitHub at this URL down below. It's relies heavily on these Trulino's libraries, which are also open source. Therefore, kind of all the pieces you would imagine would be part of a discretization code. There's libraries for discretizations, meshes, solvers, preconditioners, and so on. Also available on GitHub and developed primarily at Sandia. And with Albany being a multi-physics code, you also have a lot of other equation sets in here. So there's fluid structures, quantum device modeling, other climate modeling applications like coastal erosion and atmospheric modeling. And the benefit of this is really, if you have a new capability that's added for one of these other applications, OLI will automatically inherit them. And similarly, the other way around, if we put in something, the other applications will inherit it as well. And so you can potentially leverage a lot of work that other people are doing by having this shared software framework. I'll say there is a downside to this, namely, if someone else puts a bug in the code, then you also inherit the bug or performance degradation. So when you have a large code like this, nightly regression and performance testing is really very important. And I'll actually touch on this a little bit later on in reference to actually ICME. Let's see, the other piece here is MPAS, which stands for Model for Prediction Across Scales. Similar idea here. So MPAS is a climate modeling framework built around spherical centroidal Voronoi tessellation meshes. So they look like this. You have these hexagonal grids, so this is a little bit weird maybe for a lot of you, but this is actually very common in climate. So there's three dynamical cores that use this grid: ocean, sea ice, and land ice. And similar story where, by having this shared framework, if a new capability is added for one of these dynamical cores, the others will inherit it as well. And in terms of how we do the coupling between the two codes, so MPAS is a Fortran code, Albany Land Ice is a C++ code. So we've written interfaces between the two codes that communicate between the two languages, pass relevant data back and forth. And essentially, we currently rely on a looser sequential coupling between the velocity and the temperature and thickness, where MPAS will do the thickness and temperature solve, pass the result to Ollie. Ollie does the velocity solve, pass the result back to MPAS, and so on. And one of the things we're working on now that I won't talk about, but this is something that's work in progress, is actually trying to make this coupling tighter. So with the current workflow, it was fairly easy to implement this. But you do end up with fairly restrictive time steps to the CFL condition by doing this part effectively explicitly. So trying to make this all fully coupled is work in progress to try to reduce those, try to allow you to use larger time steps relative to what we can do now. Okay, so this is the part where I'll do kind of a series of deep dives into some of the algorithms and software comprising this Ollie model that I kind of overview just now. And so the idea here, so there's going to be a lot of topics covered. What I decided to do is I'm actually kind of going to step through all the key, not all, there's a lot, but many of the key pieces that were needed in terms of building up Ollie to have the capabilities that it needs to have for us. And I'll start with very basic things like discretizations and meshes, and go all the way to some fairly advanced things we're doing, like what's called ice sheet initialization or inversion. And the goal here is well, multifold. So first, you can see how what it takes to actually build up a code like this essentially from scratch, so that you can see some of the new algorithmic work that's possible within a pretty applied project like this one. And then, like I said before, I think the idea here is, I know that the students have various backgrounds, and so hopefully, regardless of where you are within your career and what your areas of expertise are, you'll find something that you can really sort of gravitate towards. At least that's my hope. Okay, so let's start the kind of step through the different algorithms and related parts here. So I'm going to start very basic. I wanted to start by talking a little bit about our choice of discretization, which is usually the first thing you need to think about when you're going to write a new application code based on PDEs. So we chose finite elements for this discretization, and in doing that, we actually broke with tradition in land ice modeling. So traditionally, a lot of land ice models were typically written using finite differences, and that was largely for kind of historic reasons. Glaciologists typically wrote those models. They didn't have a whole lot of background in discretizations and numerical methods. They didn't go to ICME, right? And so, finite differences was something that was pretty easy to code up. And someone started this approach to use finite differences, and it kind of stuck, and people kept repeating it. And when we came in and started this collaboration and putting in this new model, we realized that was really not the way to go. And so specifically what was happening is, with the finite difference discretization, these Neumann type of conditions we have were giving rise to really ill-conditioned matrices and causing a lot of robustness issues. And then moreover, with finite differences, you're restricted to using structured meshes, and that doesn't let you concentrate the computational power where it's needed, and really kind of reduce the number of global degrees of freedom. And so we switched to finite elements, which lets us handle these boundary conditions that we have very naturally, and allows us to use unstructured meshes. So this is an example of the types of meshes we use, which are tetrahedral meshes, and you can see they're regionally refined in the outflow, where you expect to see a lot of changes in the ice velocities. Typically, we refine this using some kind of a velocity gradient type of criterion. So I wanted to talk a little bit more about the meshes, because there's some really important nuances here that will come up when I talk about some of the other aspects in terms of solvers for this project. So if you were paying careful attention, you might actually have a question here, namely, I showed these hexagonal spherical centroidal Voronoi tessellation meshes when I talked about MPAS, and you might wonder, well, how do we deal with that? Because usually you find elements on these weird meshes, right? And so the way we do this is we actually take the dual mesh of this hexagonal mesh. So we take the dual of the hexagonal mesh, which is a triangular mesh, and then we extrude the meshes in 3D to tetrahedra to get 3D mesh. So as a consequence of this, all of our meshes are extruded or structured in the vertical direction. So that's important, because that's something we'll actually use to make use of when I talk about solvers. And then the really important detail here is that ice sheets are very thin. Okay. So ice sheets are going to be thousands of kilometers in the horizontal extent, but they're going to be only up to 4 kilometers in the vertical. And so what that means is you're typically going to have elements with pretty bad aspect ratios. So you're going to have highly stretched elements. And that's something that is going to be something we need to actually really take a lot of care to deal with when we develop solvers. So kind of the moral of the story here, just to summarize, is really it's very important to really know your problem that you're solving, to know all these nuances to see if you can potentially take advantage of them when you're developing efficient methods. Okay, so once you have your mesh and your discretization, you're going to end up with a large discrete nonlinear system for this particular problem. And so the next kind of piece here is the nonlinear solver. So I wanted to talk a little bit about our nonlinear solver and actually highlight some capabilities it has that I think are kind of cool and things that I didn't, wouldn't have known about or really thought about when I was in grad school that I learned about afterwards. So the nonlinear solver is a place where we also kind of broke with tradition. Typically, Picard iteration was used for the nonlinear solver, again, because it's kind of easy to code up. We switched to a Newton method, which ends up being a lot more efficient for this problem. And there's a couple of advancements that I wanted to highlight that I think are quite cool, like I said. The first advancement is our Newton solver uses automatic differentiation Jacobians or AD Jacobians. And so I don't know if the folks on the line are familiar with this approach. I was not familiar with this when I was an ICME student, so that's one of the reasons why I wanted to highlight this. So AD is an approach that gives you exact derivatives and Jacobians without having to take the time to derive and hand code them, okay? And so this is essentially based on the chain rule and kind of freshman calculus. So a lot of libraries are available for AD. What the libraries do is that you have, your typical operations in your code for things like addition, subtraction, multiplication, division, exponentiation. Typically, you would call these let's say doubles. What the libraries will typically do is they will apply the chain rule to each of these operations, and they will create an overloaded AD implementation of this operation that when you call it with this automatic differentiation type, it will, apply this chain rule and basically give you the derivative. And so you can use these libraries to get derivatives, Hessian sensitivities. You can even do some UQ stuff with stochastic Galerkin if that's something you want to do. And it doesn't give you any finite difference truncation error. So you get exact Jacobians. And this is really, really powerful if you have a multi-physics code and also if you want to do advanced analyses like optimization, for instance. So the other piece here is actually an algorithm that we designed that's specific to this application, but I think could potentially have some applications with some minor modifications to other problems as well that are highly nonlinear. And this is just another example of like sort of the value of really knowing your problem and trying to come up with something that really takes advantage of that problem structure. So just to introduce this problem very quickly, I have my Glen's law of viscosity from earlier in the talk. So when you don't have a good initial guess for Newton's method, you typically will use a constant, right? So when you use a constant initial guess within this mu expression, what will happen is the strain rate will evaluate to 0 because the gradient of a constant is 0. Then when you plug it in here, you're going to get not a number. You're going to get nan because of the exponent that you have. And so that's a real problem for this application. What people typically do to deal with this is they add this fudge factor or regularization term to the sum of strain squared. So just this gamma parameter, they make this very small, like 10 to the minus 10. And then they just solve the problem with this modified viscosity to get rid of the singularity. And so what we discovered is that we can actually accelerate our Newton solver if instead of fixing this gamma, we do a homotopy continuation with respect to gamma. And so what I mean by that is essentially we solve a sequence of problems. So we start gamma to be very large, like 10 to the minus 1. We're going to solve that problem. It's actually going to be close to linear because that value is going to be very large compared to the rest of this. When we solve this, we're going to take the final solution and use it as the initial guess for the next Newton solve, which is going to have a slightly smaller value of gamma. And then we continue this down to this 10 to the minus 10 value. And so what this buys us is essentially we're able to get a much faster and much more robust solve where we can cut down the number of Newton iterations by almost a factor of 2. And so this is a very application specific thing that one can do that actually helps quite a bit for this problem. So again, kind of really understand your problem and really try to look for things that you can do that can accelerate even very classical methods that are very well known and very widely used like Newton. You could potentially actually win quite a bit by doing that. Moving from the nonlinear solvers to the linear solvers, so within your Newton solver, you're going to solve many, many, many large systems, large linear systems. So, how do we do this efficiently? We typically use Krylov iterative linear solvers, so we can use both CG or GMRes for this problem since it's symmetric. And for the linear solves, there's really a lot of things that really cause problems for these land ice problems. So the bad aspect ratios are one of these problems. I'll talk more about that in the next slide. The floating ice is another problem, as it turns out. You could have certain islands and ice hinges that form that can also give rise to kind of local singularities for your linear solver. And so we've done really a lot of algorithmic work in trying to deal with these issues and come up with robust solves. And so I'm going to just highlight one of the methods we've been working on, which is a special solver based on algebraic multigrid in an idea called aggressive semi-coarsening. So I'll try to describe this fairly succinctly. But we've also looked at domain decomposition, additive Schwartz type of solvers, and we've actually worked with Professor Eric Darve at Stanford on designing hierarchical solvers for this application as well that are amenable to GPUs. So fortunately, I don't have time to cover that, but if you're interested, Professor Darve, I'm sure would be happy to tell you a little bit more about some of that work. So just to do a little bit of a deep dive into the solver that I mentioned, where I've actually was one of the contributors to this, so I decided that it would make sense to kind of highlight this in this part. So just to summarize a little bit how multigrid works for those who aren't familiar, the basic idea of multigrid methods is to accelerate convergence of an iterative method on a given grid by solving a series of cheaper problems on coarser grids. So you're going to have your initial grid, you're going to create coarse approximations, which are shown here. You're going to define what's called the prolongation and restriction operator that lets you interpolate between the grids. You're going to apply define smoothers as well, which are basically usually simple numerical schemes like Jacobi or Gauss-Seidel that you apply as you go between these layers to smooth out different components of the error to avoid the error propagating. And so what you do is you basically apply these restriction operators and the smoothers to get to the finest grid. You're going to solve your problem on the finest grid. You can usually do this using, something like even a coarse solver, since it's a direct solver, since this is going to be such a coarse small problem. And then you apply the prolongation operator to get back up to the fine grid again, doing these smoothers to smooth out various components of the error. And you're essentially using this solution on the coarse grid, prolongated up to the fine grid to precondition the fine grid problem. And so we're looking here at algebraic multigrid methods, and what that basically means is that you're doing the coarsening at the level of the graph of the matrix rather than actually having to form these meshes. So that's kind of the whirlwind overview of multigrid. So what's the problem with applying multigrid kind of off the shelf for this application? Well, the problem turns out to be these bad aspect ratios. And so the reason this is a problem is when you apply standard off the shelf multigrid, you coarsen equally in all three coordinate directions. And what happens is when you're doing that and then you're applying these smoothers to smooth out components of the error, it's very hard to do that in the horizontal direction because of there being relatively small horizontal coupling terms due to these highly stretched meshes. And so as a result, the solver really doesn't work very well. And so what we realized is that no matter what kind of solver you design for this application, you really need to take advantage of these layered nature of the meshes and these bad aspect ratios. And so what we do is we take advantage of this extruded or layered nature of the meshes. The algorithm we designed is shown here at the right in this cartoon, where essentially you're just coarsening in the vertical direction until you're down to a single level. And after that, you can coarsen in an unstructured way because you're essentially just in 2D and you've gotten rid of all these bad aspect ratios. And so that's kind of the algorithm in a nutshell, again, taking advantage of kind of problem structure. And the solver turned out to be one of the new algorithmic outcomes of this project that we've also applied to other application areas that are characterized by thin structures with layered meshes in the thin direction with very good results. So this has actually been made available as a part of several Trilinos packages and has impacted other application areas as well beyond just this land ice modeling one. So some results for the preconditioner. This is a weak scaling study for Greenland. So we're taking a coarse problem, 300,000 unknowns on 4 cores, scaling this up all the way to 1.12 billion unknowns, 16,000 cores, keeping number of degrees of freedom per core about the same. So it's a weak scaling study. we're plotting CPU time as a function of the number of cores. And so you want to see these lines be basically flat. And so if they're flat, that means this is scaling well. And so you can see, you know, we're getting good scaling. It starts to decline a little bit on the finest mesh, but that's actually expected for the largest problem. Comparing in this here, I have an ILU rather than a standard multi-grid, but you know, similar idea where we're able to get a much more scalable and fast linear solve. The linear solve piece here is in red. We have other pieces as well. Finite element assembly is another part of our computation, but that wouldn't be affected by the design of the preconditioner. Where you really need the new preconditioner, as it turns out, is Antarctica. And so to understand why, it requires actually a lot of analysis using Green's functions. And so I'll try to explain this pretty succinctly, but you can find a lot more detail in the CISC paper from 2016 by my colleague, Ray Tuminaro. Excuse me. And so the idea is basically, if you look within the ice shelf, the boundary conditions you have for the floating ice, if you look at how the Green's function will look like here, this is how it's going to look like. In particular, it's going to be approximately constant in the thin direction. And the reason that this is important to look at is these Green's functions are related to matrix inverses. And so when you have a Green's function that looks like this, that means your A inverse is going to have a very large number of non-zeros. And so what that means is that if you try to use an ILU preconditioner, it's not going to be able to approximate that inverse very well. So that's kind of my you know, elevator speech type of a description of why the ILU doesn't work well for these types of problems. A lot more detail in the paper again. And indeed, if you try running ILU here, you can see that it actually doesn't even converge for the finest problem, whereas we get a nice fast scalable solve using the AMG solver, which doesn't have this issue. Okay, so moving from performance to performance portability. So just a little bit more on kind of software rather than numerical algorithms, although the algorithms are relevant under the hood here as well. A big requirement for our model was to be able to run the model on new architecture machines. So hybrid systems, many core devices, multi-core CPU, GPU, Intel Z and Phi. The model we're using to achieve this performance portability is what's called the MPI plus X programming model. So you basically have two levels of parallelism. You have MPI for internode parallelism, and you have the plus X for intranode parallelism. And basically within each MPI process, you're going to launch many threads to speed up your calculation beyond what you would have with just MPI alone. And so we're primarily relying on a library called Kokkos to achieve this performance portability. And so this is a C++ library that essentially enables us to just write an algorithm once using Kokkos functors, so that if you want to run the same algorithm across various architectures based on this memory layout abstraction that exists within Kokkos and this templated metaprogramming, you essentially can compile your code for different architectures that you are running on, and thereby get good performance without having to actually modify your code. So the optimal data layout gets selected at compile time. We've had a big effort to port the finite element assembly within Albany to use Kokkos functors, and actually there's a Stanford alum, Jerry Watkins. Some of the folks online may know him, the faculty, for instance. He was in the Tony Jameson student in AA. He's kind of leading this effort along with me. He was my student postdoc and now staff in my department. And we've also been working with the solvers team within Trilinos on portable solvers for this application, and also beyond Trilinos, like I mentioned, Eric Darv was one of the other collaborators. We've been working on the solvers. So just to show a little bit kind of how Kokkos actually works, this is more kind of code again rather than numerical algorithms. The point here is that this is very easy to use. So this was a routine in Albany that computed the gradient of a vector. So there, we can pretend this is not crossed out, which is how this was originally. You have loops over cells, quadrature points, dimensions, and so on. So you're going to want to take each of these things and you're going to try to give it to a thread to compute this all massively in parallel for some of these loops or one of these loops. So if you want to just do it for the cell loop, you remove the loop, you add a Kokkos parallel 4. It's templated on this execution space parameter, and that's the parameter that tailors this to the device. So you can you basically set it at compile time to get the optimal layout, like I mentioned. And so we've been able to run the code successfully with reasonable scaling across a variety of architectures, including GPUs, so Intel Sandy Bridge, Intel Skylake, IBM Power 8, Power 9, Kepler, Pascal, Volta, Ampere GPUs, KNLZ and FEES. We're already running the code on Summit, the largest supercomputer having this Power 9 architecture and Volta GPUs, and really going forward, the future is GPUs. So future targets will include some of the other kind of up and coming machines at the lab, Aurora, which will have Intel GPUs at Argonne, and Frontier, which will have AMD GPUs at Oak Ridge. And I wanted to highlight something here that I alluded to earlier. So, when you have this large code, right, that has a lot of dependencies and it's constantly changing. One thing that's really, really critical, and it doesn't sound like it's the most glamorous thing, but it's really incredibly important, is regular regression and performance testing. And so I wanted to highlight this because this is something that an ICME Explorer student helped us with last winter, Kyle Shen. He did a project with us under the CME Explorer program, which I believe is CME 291, or at least it used to be. And so what the project was looking at is taking our nightly performance data, which gets automatically generated on different platforms, and applying change point algorithms to try to determine if there were significant improvements or degradations to the CPU time, again, across these architectures. And so this is some output from that tool. You can see, for instance, in April of last year, something happened that slowed down the code substantially, and we noticed it based on this. And then after a few, maybe a week or two, we were able to get it back down to how it was. And so, this sort of thing, again, you typically, as a student, you're focused maybe more on the algorithm or getting your code to run. But this is really, really critical to be able to do this kind of testing and performance monitoring to make sure that things don't get broken. And, you will get burned if you don't do something like this especially for a large application. Okay, so then this is really kind of the last topic here. The UQ is a little bit more of just a teaser, but this is something that I think is really quite cool. And I've also alluded to this a few times, this ice sheet initialization. And this is really more of an advanced capability we have. And that really makes this model that we have unique relative to other models. And so what is the idea of this initialization? So I already mentioned we have certain parameters in our model, like the basal friction, that cannot be measured. The idea here is that we want to basically find those parameters in a physically consistent, rigorous way to start off one of our dynamic simulations. So that's what we call initialization. We want to find the ice sheet initial state that matches observations, matches present day geometries in equilibrium with climate forcings. There's a lot of data available for this actually, but most of the data is at the top surface, ice extent, surface topography, surface velocity, surface mass balance, sparse measurements of ice thickness. And so we want to estimate fields like the basal friction, and we want to fill in the thickness where we don't have it. Typically, the way this was done was with a really kind of crude ad hoc type of an approach called a spin up, where you kind of guess your initial condition, you run the model for many, many years, you try to kind of fudge the initial condition to get it to match observations. And when you're happy with how it looks, you stop and you use that as the initial condition. And this is very imperfect, so it burns a lot of CPU time. You can also get pretty bad shocks that can initiate large transients and derail some of these simulations. And so we did this in a much more rigorous way. And so we do this by basically formulating and solving a PD constraint optimization problem. So here's how the problem looks like. We're going to minimize an objective functional M subject to your first order Stokes equations as the constraints. You're going to solve this for instance, basal friction thickness. You could add other parameters too. And the mismatch has basically these terms that are trying to match your computed solution to the observations on the boundaries where you have the observations. So we have three terms here: surface velocity mismatch, surface mass balance mismatch, and thickness mismatch. The addition of these two terms was something new that we came up with as a part of this project that improved the results. So that was another kind of new algorithmic aspect here, this formulation and ways to solve this and the resulting initial conditions and results we got from this formulation. And this has the effect of significantly reducing the non-physical model transients. So that's really important for this. So I think I'm kind of running low on time here. So let me try to kind of speed up a little bit. So we solved this through an embedded adjoint-based PD constraint optimization algorithm in OLLI. The adjoints are a way to basically get gradients of our mismatch function very efficiently by solving the adjoint equations, which are linear for us. And we rely on the automatic differentiation for the adjoints, which helps quite a bit to put this in. And we're using a library called Rapid Optimization Library to do this actual optimization. Just a few results to give you a sense of the what this gives us. So what we did is we inverted for an initial condition. This is for a fine resolution 1 kilometer Greenland problem. We did a forward solve using that initial condition compared to observations. These are the observed and computed solutions. They look virtually the same, and the error is quite small as well. If we add these extra terms with the surface mass balance, and we're able to match that field better relative to observation. So that's kind of what you would expect. And this inversion is the real deal. So we routinely use this for realistic initial conditions for some production type of runs. Done this on about 1 million parameters, I think, was the smallest or the largest problem. And I don't really have time to go into this, but just to mention, we're working on doing a fully coupled velocity temperature solve in order to be able to do this inversion together with the temperature, which in our case we have an enthalpy equation. And to do that inversion with the temperature, we basically add the enthalpy PDE to our constraint, and that allows us to get a self-consistent temperature velocity initial state all in one shot. And that's really an unmatched capability, because typically other models would have to spin this up for tens of thousands of years to get it to equilibrate, even if you do the inversion for just the velocity. So then this last part here, this is really just a kind of a teaser. So UQ is a big part of this project, and we've done a lot of work on this. And this is the only slide I have on UQ, and there's no real kind of content here. And the reason for this is quite honestly, we've had this multidisciplinary team with lots of experts. We've worked on this for many years, and we still don't have a good solution for the UQ. So if you're kind of a UQ person, this may be kind of interesting what some of the challenges are. So one of the challenges is the fact that, actually, let me go to the next, yeah, there we go. One of the challenges is that is the cursive dimensionality. So our inverse problem that I just talked about, if you wanted to do this in a Bayesian framework, so to take into account measurement error or noise in your observations in this inverse problem, your parameters that you're inverting for the basal friction, let's say, they're going to have hundreds of thousands or 1 million dimensions. And so, how do you explore this huge parameter space? And we've tried various things. None of those have really kind of panned out so far. So we're still very much working on this. But if you're a UQ person, this is definitely a problem to try to tackle. So I'd be happy to try to if you want to talk about this offline, we can talk about some of the things we've tried and kind of why those things haven't panned out. So I know I'm kind of over time here, although we did start a little bit late, my defense. Let me just very quickly show you some movies here that we've done, and this is a little bit more like kind of eye candy, just because it's a computational talk. There's a lot of papers and presentations with kind of science results that are a little bit less maybe glamorous, but very very interesting nonetheless. So the first thing we did before doing really science runs is validate the model using 2 satellites, ICET and GRACE. And I don't have time to go into this, but there's a paper in GMD from 2017 that details some of those comparisons. So this is one of the simulations I wanted to show. This is what we call the ABUMIP-Antarctica Experiment. This is Antarctic Buttressing Model Intercomparison Project. That's what ABUMIP stands for. What the idea here is you instantaneously remove all the ice shelves from Antarctica and you prevent them from ever forming again, and you run this for 200 years. And this is not a realistic problem, but it's important because it provides an extreme upper bound on sea level rise contributions from Antarctica. And so as this runs, if you were paying attention, you can actually see this buttressing effect. So it'll start again, and you'll see. So when the ice shelves get removed, you're going to see, so that it's gone now. You see all this rapid loss, and this is that phenomenon that I was mentioning with the buttressing. You really see it in the simulation. And so we were able to do this very robustly compared to other models, even though this is a very high fidelity kind of fine resolution grid. That's how your final Antarctica looks like. There's another experiment called LARMIP, and I think I'll skip this, but there's a it's less extreme. You just prescribe warming under one of the ice shelves called the the Fulcan-Orani ice shelf. There's a really nice annotated video with voiceover on YouTube that describes this whole thing and some additional experiments that were done. So I think I'll maybe just point you to that in the interest of time. We participated in model intercomparison projects that ended up in a Nature publication, looking at kind of probability density functions of, you know, from different models, what sort of configuration, what sort of predictions you get for a suite of models that participated in this experiment. And this is a regional simulation of the Thwaites Glacier in Antarctica under parameterized submarine melting. So it was a sort of a UQ study where you're looking at different basal melt rates and how that affects the ice shelf base depth. Details are in this paper from 2019. But what's interesting is you can see in this movie, this is not anything crazy like the ABUMIP Antarctica. This is sort of present day initial condition business as usual for one of these ensemble members, and you can see a pretty substantial decline in this ice shelf as I run the movie. Yeah, this is, we are able to run kind of partially coupled to the E3SM. So these are just some kind of fun movies from the ocean side when we're running the coupled ocean simulations. So I think I'm out of time here. So you know, hopefully I you know, was able to convince you that actionable projections of climate change and sea level rise are important worldwide. You know, I talked about this mature ice sheet modeling capability we've been developing focused on equations, algorithm software. So, you know, the hope was to sort of cover something that, you know, all the audience members would be able to, where, you know, at least one of those things the audience members would be able to really resonate with. References here, I'll mention, we also, this has been a really high profile project for us. So you know, myself and other team members have been interviewed for different general audience articles, and there's that YouTube video that I mentioned, and these are linked on my website if you'd like to kind of check these out just to get a sense of the project more at a high level. Gianluca, would you like me to do I'm sorry, this went a little bit longer than I expected. I had a few slides prepared on some of my ICME perspectives. Did you still want me to go through that really quick, or?
Maybe really quick.
Okay.
I know that unfortunately some students have a conflict coming up, so I know
okay.
many will be leaving very, very soon, but you know, but this was great, by the way. Actually,
I was expecting it went a little bit slower than I guess with the virtual.
Okay.
It's a little bit hard to keep track of it. So let me just I have a few things that I thought, you know, so Gianluca asked me, since I'm a Stanford alumna, to share a little bit on my perspectives on Stanford and ICME. So I have a few slides on this. And so just to kind of recap the intro, so I was an ICME PhD student from 2006 to 2011. I was Professor Charbel Farhad's student. I worked on this discontinuous enrichment method for convection dominated flow problems for my thesis. And I put some pictures here, you know, from the beginning and the end. So, you know, I had an office in the basement of Durand. This is what it looked like. You know, not very glamorous. We had a lot of whiteboards, no windows. So we created our own window, my office mate and I. And, you know, this is kind of where we started. And you know, finally the graduation, you know, 5 years later with Liz Charbel, and there's some other students here like Kevin Carlberg, Julian Cortiel, that Gianluca may recognize. But one thing I wanted to say is that one thing that was kind of unique about my experience at Stanford is I was concurrently a year-round intern at Sandia in Albuquerque in the Aerosciences department while I was at Stanford. I spent four summers there, and I worked on a project that was different from my thesis work. So I worked on projection-based model reduction for compressible flows. And I mention this because I think this experience really helped shape me as a researcher and helped me really figure out, you know, what sort of research I wanted to do and what I wanted to do after I graduated, which ended up being at the labs. And I mention this because I did get kind of pushback from various people I consulted with about this, you know, Stanford and around, you know, both students and faculty. You know, these are prime research opportunities. You should stay at Stanford. It's going to delay your graduation. And I very much disagree with that. So I think effectively as a result of this experience, I had kind of two areas of expertise when I graduated. I had a lot more connections that helped me get started on my own independent career. And I also got to do some cool stuff in New Mexico, like go to, you know, Bandelier National Monument, White Sands National Park. So these are some pictures from that. It's not non-technical, but nonetheless important in terms of helping you kind of shape what your interests are. I really do think that ICME prepared me very well for a wide range of engineering and science program problems that I've worked on. So I talked about ice sheet modeling today. I've done modeling work in other climate areas like erosion modeling and atmospheric modeling. I worked on model reduction for captive carrying reentry environments, multi-scale modeling methods for component failure analyses, developing some new enriched method for enabling advanced armor impact simulations for the Army Research Lab. So lots of very cool projects that I've had a chance to work with. Today's talk was just one of them. This is kind of a summary of the courses that I took that I thought were very useful, and the ones in bold are the ones I thought were particularly useful, and you'll notice the core courses listed here at the very top. And I think maybe this bottom part is a little bit more important than the top one. So there are things looking back that I wish I had taken and learned more about. So the software engineering for large HPC codes is a big one, not very glamorous, but very, very important. More on this next gen architectures, more on these advanced optimization topics, more on Q machine learning. Some of these things hadn't quite taken off while I was there, but I will say that, admittedly, some of these things I was interested in, but I sort of maybe was a little bit intimidated by them at the time, and I kind of passed on that opportunity at the time. And my advice would be that if you really want to learn something, and you're just maybe scared or lazy, or you should really, I would recommend to do it. And those are the types of things that you maybe regret, or the opportunities that you miss, not usually things that you kind of did if provided with something you really wanted to do. So that's I think something I would tell my younger self looking back. As I alluded to, we do hire at Sandia. So labs weren't on my radar when I started at Stanford. I would encourage students to consider us. We have 2 locations, one in Livermore, one in Albuquerque. I've been at both locations. We are a weapons lab, but we do a lot of research in climate as well, as I showed you today. It's really a great place to work. Lots of interesting problems requiring fundamental research in math and computational science, great work-life balance. And we hire interns. We actually, I have an Explorer project right now proposal, if you want to check that out, if you're thinking of doing that. It's related to this project. So we have some colleagues of mine have projects as well. Postdocs, we have some prestigious postdoctoral fellowships, von Neumann, Truman, and Kruby, that let you design part of your own research program as a postdoc and for staff. And usually for staff, you need a citizenship, but for the other opportunities, we do hire foreign nationals. We can hire foreign nationals. So I'll stop there, and I really apologize for going so late. I wasn't quite expecting to for it to take so long, but I'll stop here. And if there's still folks online and they want to ask questions, I'm happy to stay longer and try to answer them.
Well, thank you very much, Irina. This was phenomenal, really, really nice.
Thanks.
There have been a few questions on in the chat, so maybe we can start from there. I don't want to impose on anybody. I know that many of you have to leave, so obviously feel free. But there were a couple of questions. Maybe I'll summarize them this way. One was about you talked about average increase in sea level, but the question was how is there a metric that is perhaps weighted more carefully related to impact of perhaps certain areas? 1 millimeter might be as painful for other areas. 1 meter might be more painful in other areas. So
right, I understand. So I think the important thing to recognize about this statistic, and I didn't say it on that slide. I thought to say it, but I didn't. So the range of 0.3 to 2.5 is quite large. So I think that's an important thing to recognize, because that tells you actually how uncertain and how varied the models are. So certainly, yeah, I totally agree that in a certain place where you maybe have houses right on the beach, you're gonna maybe have, this would be a larger impact than if you have like a big levee or something there, if that's what you're getting at.
That's right.
So I think this is a more of like an risk management type of question. And I think that the idea is that we're scientists, where we provide these predictions, and we would give this data to actually policymakers, and then they would help to kind of process this. And obviously it would be dependent on the location and what's important there. And I'll actually make a joke here that I've given this talk, you know, in landlocked areas as well, not the Bay Area. And what I usually say there is you know, if you're living in, you know, Illinois or something, you might think this is not important, but then when all these people from Florida and New York and San Francisco start moving into your city, maybe you'll care.
Yeah,
So,
New Mexico is a great example as well.
yes, that's right. Right.
So there was another question related. You mentioned machine learning, and you're right. When you were on campus, obviously this was just starting, so there are more opportunities now. But there is also a lot of opportunities on doing research in machine learning, especially for physics-based models. So is there any consideration of sort of specific aspect of machine learning that you guys are interested in these problems?
Yeah, no, absolutely. So I think, so I'm looking at the question now in the chat. You guys can probably see it because I'm still sharing my screen. So the physics-informed approaches. So I like the physics-informed machine learning approaches in general because you don't throw away the PDs. I think that there's a lot of promise in using machine learning to learn some of these physics. So for instance, we assume this constant basal friction in the boundary condition. You can also assume a functional form for it, and people do this. It's called a hydrology model, and there are parameters there that aren't really known. And so trying to use available data to learn those parameters, or trying to use available data to learn calving laws for how the ice sheet will break off in the periphery, I think. So my personal opinion on machine learning, so I do like the physics-informed machine learning approaches. I don't, and I like the idea very much of where you don't know something, you don't know a law, you don't know a PDE, or you don't know some parameters in the PDE, and you have data trying to learn those parameters. I think there's a lot of value there. I'm kind of less impressed with the idea of sort of like throwing away the PDEs and using a machine learned model. I think if you kind of know the PDEs, you should try to use that information as much as you can. But yeah, I think in terms of learning these parameterizations and these physics, as they're called, and you know, potentially also with within the UQ trying to come up with some you know, cheaper surrogates. There's actually a huge effort right now. It just ended, but the DOE had a call for white papers it's called AI for ESP, and I think ESP is Earth. See, I don't remember it now. It's Earth Science Program, something like this. So it's basically for climate modeling. So looking at new ideas for using AI for climate modeling, and some of my team members did put an idea on using machine learning to learn these parameterizations. So this has been recognized as a big thing to try to do for climate models that a lot of the program managers are pushing people to get into the machine learning and seeing where that can be useful. By the way, our Explore project here that I mentioned, this is actually potentially using machine learning, but in a very kind of different way, I think, for most people, which is actually to use machine learning or other data-driven methods to try to learn optimal solver settings for running our model. So it's I think different than what most people think of when they think of using machine learning, but kind of interesting. So check that out if you're. Sorry for my shameless plug there again, but
no, actually, thank you for mentioning it. I should have, you know, Karen and Carrie, you know, were asking me to remember the Explore project, and I forgot. So I'm glad that you mentioned this. Okay, well, maybe quickly, you're looking at the chat. There was another questions about accuracy. Maybe you can comment on that. And...
So, okay, so Navier-Stokes, so the thing is, okay, so Navier-Stokes are not relevant here. And this is because you don't really have advection. It's really just creep of the model. So we're not losing anything in not doing Navier-Stokes. Navier-Stokes isn't really the appropriate set of equations. In terms of, I think that maybe the more relevant question is you know, the full Stokes that I mentioned versus this first order Stokes model. So there is some difference in the solutions you would get in certain areas, and there's certain types of glaciers that the first order Stokes equations aren't able to predict as well as the full Stokes. But actually that model is considered. I don't have a quantitative number. I think this could be looked up, or I can ask a glaciologist. But in general, those equations that we're using with the 2 unknowns per grid cell, they are valid at the continental scale, so for both Greenland and Antarctica. And other models out there, like the one in that bicycle's dynamical core, they're actually only valid for certain types of problems. So those equations are only valid for Antarctica, and there's other models that are only valid, for instance, for shallow ice or for shallow ice shelves. And that's not the case for the first order Stokes. So it's sort of the highest fidelity of the lower fidelity models, if that makes sense.
Okay, very good. Well, I think we're gonna stop here. I really appreciate you spending time with us this afternoon. I think this was a certainly fantastic mixture of algorithmic challenges and really physical impact. Very interesting project, and I think everybody can really appreciate your the level of passion also that you put into all of this. I think this was very engaging. Thank you very much for the time and participating.
Feel free to reach out to me. I actually live just across the bridge at Union City, so but everything's closed now. But if you do have additional questions, feel free to email me, or connect on LinkedIn or whatever, and I'm happy to try to answer and connect with you.
Absolutely.
I've had good experience with Stanford students.
Great. Well, thank you again, and well, hopefully we'll be in touch, soon and in the near future for other opportunities. But I'll definitely, if anybody contacts me, I'll send them back to you so that you can, perhaps engage with them afterwards. So thank you.
Perfect. That sounds great. Thanks so much.
Thank you all. Thank you.
Bye.
Bye-bye.